Okay, we're going to be looking into rational expressions, and with rational expressions you're looking at varieties of fractions. And to start us off, okay, with rational expressions, now we have a theme that's going to be recurring time and again, and this will be within what's going to be referred to as the domain of a rational function. And now for what we have in line with the domain, you're going to have what is regarded as a restricted value. And now for a restricted value, okay, those are going to be regarded as situations where you have a value that is going to render a rational expression as undefined within the real number system. Okay, so you have a value. It's going to render, again, a rational expression as undefined in the real number system. And just the rule of thumb for what we have in the case of restricted values, okay, for rational expressions, again, let's say just for the common rational expressions, those would be values that would cause the denominator of a fraction to be equal to 0. And in fractions, for fractions to be real values, you can divide by any number except 0. And let's say that if you're looking at determining restricted values, and we'll say that we have for first case here, let's say we have a fraction such as 3 over x. Again, for 3 over x, for this to be defined, the bottom part of the fraction cannot be 0. So x cannot be 0. So the restricted value is 0. Let's say we have another rational expression, and let us say that we have 4x over x plus 7. Now we have two expressions in x, one in the numerator, the other in the denominator. And again, the restriction is going to come from the denominator. So we have x plus 7 cannot be 0, and if that is the case, then x cannot be negative 7. So we have the restricted value to be negative 7. Now let's say if we have another rational expression. Let's say we have 4x squared plus 3 over x squared plus 10x minus 24. Again, the restriction is going to come from the denominator. So we have x squared plus 10x minus 24, which cannot be 0. And if we look into factoring, so factors of this trinomial will be where we had the quantity of x plus 12 times that of x minus 2. And if the trinomial cannot be 0, well, neither can either of the factors. So we have with the restrictions, x plus 12 cannot be 0, so x cannot be at negative 12. For x minus 2 also cannot be 0, so x cannot be positive 2. So we're going to have for restricted values negative 12 and positive 2. Now let's say if we cross over to operations with rational functions. And let's say that if we're adding a couple of rational expressions together that have the same denominator, okay, and we'll say that we have 2x plus 3y, 2x plus 3y over 4, and say we have minus, and we'll say that we have okay, so we have minus 8y plus 9x over 4. Now we had the same denominator, and if we look at combining numerator terms together, so we have 2x plus 3y. You notice the second fraction follows the subtraction that is in the middle. So once we combine numerators, both the 8y and the 9x will be affected by the subtracting. So once we put it all together, so we have 2x plus 3y minus 8x, or make that minus 8y minus 9x all over 4. And combining like terms, so we have 2x minus 9x, so we have negative 7x. 3y minus 8y, we have negative 5y over 4. And this is one way that the expression could be given. Now some books might have it as, say, the negative of 7x plus 5y over 4. So that's like negative 1 times 7x plus 5y, which would yield negative 7x minus 5y, okay, over 4. And let's say that if we have, for operations with rational expressions, let's say in the case of combining fractions, and we'll say that we have ratios such as 1/10, 1/16, and 1 over 100. And to be able to add together, we need a common denominator. And let's say that in terms of least common denominator, okay, we have posed the question, okay, just what is the smallest number that 10, 16, and 100 will go into? Well, in the case of what we have with the number 10, 10 can factor out, and prime numbers, prime factorization of 10 is going to be 2 times 5. Now for 16, regardless of whether you have 2 times 8, 8 times 2, or 4 times 4, you're going to have prime factorization, whereupon we're going to have 2 as the prime factor. So 16 is going to be 2 times 2 times 2 times 2. And for 100, and the pathway created in terms of reducing to only prime factors, so we have 10 times 10. And just like the first 10, we have 2 times 5, 2 times 5. If we put together and just resequence, so we have a couple of 2's and a couple of 5's. And for what we have in terms of the least common denominator, now we got prime factors with 2 and 5. And for the least common denominator, okay, you're going to take the highest degree representation of each, or the most common appearance of each prime factor. Okay, so we have with 2, it appears only once for 10, 4 times with 16, 2 times with 100. So we have 4 2's. In the case of the number 5, it appears once, then not at all, and we have twice from 100. And if you multiply what we have for the 2's and the 5's, okay, we're going to have at 400. So in taking what we have now, say have 1/10, and raising in terms of the denominator 400. So you got multiplied by 1 in the form of 40 over itself. Now we got 1/16. 16 into 400 is going to be 25. And for 1 over 100, into 400 is going to go 4 times. And once we combine, okay, so we have 40 plus 25 plus 4 all over 400, and we have with the total, okay, so we end up with 69 over 400. And again, so we have 1/10 plus 1/16 plus 1 over 100, and again we have for the total, we have 69 400ths.